All right, welcome back to Finite Element Methods, class number 5, Math 574 here at the University of Tennessee. We discussed the notion of weak derivatives last class. We showed this sort of generalization of the concept of derivatives and showed that functions that are um, not differentiable in the classical sense, like a function like a function which looks like that, say, which is not differentiable in the classical sense because it fails to be differentiable at 3 points, is nonetheless weakly differentiable if we expand our notion of what it means to be differentiable. We based our definitions of weak derivatives on integration formulas. In fact, we used the integration by parts formula to derive our definition. From this, we're going to be able to build a whole world of interesting new function spaces called Sobolev spaces, which we'll now talk about. So, um, what is a Sobolev space? Basically, a Sobolev space is a collection of functions from an LP space such that their weak derivatives are all also LP functions. And the derivatives, if we say that the derivatives of order up to and including order k are weakly differentiable and in LP, then we call these functions the WKP functions. So k is the number of derivatives that you're allowing, and p is the type of LP space that you want to use. You can use any type of LP space from 1 all the way up to infinity, inclusive of infinity. Those spaces, remember, are the essentially those spaces whose essential supremum is bounded. If you've never seen that, don't worry about that too much. It's not a big issue. I think you all probably know what we mean by LP spaces, though, where P is between 1 and infinity, but not inclusive of infinity. Okay, so these are all based on integral formulas or integral norms, integral-based norms. So our concept of an Sobolev space, generally speaking, the thing that we'll be interested in here is a set omega, which is a subset of, this should be RD, that is both open and bounded. Here, I'm only defining this for open sets, and I'm not requiring that omega also be bounded. But for the most part, here in this class on finite elements, that's the situation we're going to be interested in. The open set is also going to be a bounded set. And furthermore, we'll get into this in a little bit. We're going to assume that these sets have fairly nice boundaries. In any case, these are what we call the KP Sobolev spaces. Again, they're spaces of functions which are LP functions, such that the weak derivatives exist and are also themselves LP functions for all weak derivatives up to and including order kth derivative. Okay, these are the KP Sobolev spaces. The norms on these spaces, well, these depend on whether we're using the the P spaces for between 1 and infinity, not inclusive of infinity, or if we're interested in the P equals infinity case. So these guys, where P is between 1 and infinity, not inclusive of infinity, those are based on the integral norms, integral-based norms for the LP spaces. And the norm for this space is defined in this way. So what we're going to do is we're going to sum up, okay, the norms of all of the derivatives, okay, of V, of all orders up to and including the kth order derivative. We're going to take the LP norm of each one, and then we're going to take that to the P power. Okay, so you remember what those LP norms look like? So just to refresh your memory, so this is the basic LP norm. You take the integral of the absolute value of the function to the p power, and then you take the 1 over p power of that. So if I raise that to the p power, of course, that just gets rid of this 1 over p power. Okay, so that's what we mean by the p power of these LP norms. That's exactly what we're using there. And we're taking all of the derivatives of all orders up to and including the kth order derivative, taking the LP norm and raising to the p power. So that's where we're getting. Then finally, after we've summed up all of those, we take the 1 over p power. Okay, and you can you can check that this satisfies all the properties of a norm. Now, for the p equals infinity case, remember L infinity, that is the space of Lebesgue measurable functions such that the function has a bounded essential supremum. Again, if you don't know what that means, don't worry about it too much. Just think this is the maximum of that function. So you take the maximum of all the functions, of all the derivatives of the functions, of all orders up to and including the kth one, and then we take the maximum of that, okay, the maximum of that max. Okay, so we're mostly going to be interested in the case where p is equal to 2. So you won't have to worry too much about any of that stuff because we're only going to be interested in p equals 2. And remember, we're not doing this in the abstract setting. We're not really interested in the abstract version of all these Sobolev spaces, and we're definitely not interested in abstraction for the sake of abstraction. We're interested in concrete calculations ultimately. And mostly, we're going to be interested in this case where p is equal to 2. So in that case, we write, instead of WK2, we're going to write HK because these are what are called the Hilbertian Sobolev spaces. This is the case where p is equal to 2. This latter space has an inner product associated to it, which gives rise to this norm. So that would be the case where this p is equal to 2 and this p is equal to 2, so this would be the square root. So the inner product in that case, the so-called inner product on HK, this is an error here, it should be HK. The inner product, remember an inner product is always a function of two separate functions, two functions coming from the space HK. So we're going to take two functions, u and v. You can call them points of the space if you like. But an inner product is always takes two and gives you a real number from that. And so the way we're going to calculate this inner product is if we're going to sum over all the derivatives of order up to and including the order k derivatives. We'll take the weak partial of u against the weak partial of v, and we'll take the L2 inner product of that. So this is just going to be an integral, right? So this with that, remember what does the L2 inner product mean? So let's go back up here, L2 inner product, just to remind you, uv L2, that's just going to be integral over omega of u of x, v of x, dx. So that whenever I take u in the first and second position, this becomes u squared. And if I take the square root of that, that becomes the norm. The same thing happens in the Sobolev space setting. What I'm doing here is I'm adding up the inner products of all the pairwise derivatives of u and v, up to and including the order k derivatives, taking the L2 inner product of each one of those. And if I want to get the norm, what I do is I take the square root of those norms. And I got typos everywhere. This is not h2, but it's h to the k. Right? K is the order of the derivatives that are allowed, and I'm going all the way up to the kth. Now, if I stop at k equals 2, that would be h2 here. If I stop at h1, then that's h1. Okay, so these are how I'm defining my Sobolev spaces, and I'm claiming that these are the norms on that spaces, or that gives rise to a norm. And then finally, I'm claiming that these Hilbertian Sobolev spaces are actually have an inner product associated to them so that they can induce a norm in the usual way. Okay, so the first thing I want to show you is, well, the first thing we ought to really talk about is this really a norm? And the answer to that question is yes. I'm going to leave that to you to show that these are actual norms. And the fact is, we know already that the norms that I erased up here earlier, the LP norms, are in fact norms. They're the standard good and true norms on LP spaces. So we use those facts, and it's pretty easy from that to show that these are in fact norms. Okay, or in other words, this is a norm on that space. The next thing I want to show is that the next thing that would be after that would be to show that these Sobolev spaces that we've conjured up are actually Banach spaces. So what does that mean? That means that if I have a Cauchy sequence in that space, then that sequence, then there's a limit point which is also in that space, so that Cauchy sequence actually becomes a convergent sequence, and the limit of that sequence is that point. So the way we are going to do this is suppose that Vn is a Cauchy sequence in the space WKP. All right. Again, this is I mentioned before the start of class that my treatment of these Sobolev spaces is coming by this rather well-known book by Atkinson and Hahn called Theoretical Numerical Analysis. And this proof is pretty much taken verbatim out of that. So let's let Vn be a Cauchy sequence in this thing I want to show as a Sobolev space. So what do I have to show? I have to show that this thing converges in the norm that's on that space. So now the fact that this is a Cauchy sequence means that each one of these elements is in WKP. So what does that mean? That means that certain things are true about this. So what do we know? We know that each one of these, for every n, it has a bunch of weak derivatives up to and including order k derivatives, right? So what I can show then is for any multi-index alpha, where the multi-index order, the order of the multi-index is less than or equal to k, then the sequence of the derivatives of this guy, the weak derivatives, and by the way, I've started dropping the subscript w in this lecture because we don't really need to add that extra bit of notation. So every derivative that you see is going to be a weak derivative unless it's known that the function is classically differentiable in the usual sense. Well, what we can show is that if this is a Cauchy sequence, then each one of the sequences of its derivatives, all the partial derivatives up to and including the kth order partial, is or are Cauchy sequences. Each one of those are Cauchy sequences, and in fact, they're Cauchy sequences in this space LP. So what's the first, the first thing I want to say is, and make sure you understand is clear, if alpha has order 0, that means I'm taking no partial derivatives at all, then that just means the original function itself. Okay, so if I say something like this, where the order of alpha is equal to 0, then that's just the function itself. So all the function, all of its derivatives up to and including the order k derivatives, I'm saying are Cauchy sequences. So the function itself and all of its partials. But now we know that LP is a Banach space. This is a classical result known from measure theory, that all the LP spaces, and here we're mostly interested in the standard ones, p between 1 and infinity, but we could also go up to infinity as well. But a lot of people have never seen LP spaces, they're not as comfortable with the p equals infinity case. So for now, you can just drop that. We're not going to We're not going to need too much of it. But in any case, it's a well-known result that these LP spaces are Banach spaces. So for each one of these sequences, there exists a function which I'm going to call V sub alpha. Okay, now this might not have any relation at all to the original, to this original sequence. Okay, so there's some V alpha in LP such that the derivatives of Vn converge, the alpha partial derivatives of Vn converge as n goes to infinity to these functions V alpha. Okay, and now each one of these V alphas has to be unique functions because this is the way it works. If you converge in the space, then the limit point has to be unique. All right, so, and by the way, this convergence is in LP. So that what that means is what we know is, oh, I was going to write it, but I've already got it written here. So this is what we mean by convergence in the space. The norm of the differences for each n, okay, converges as, right? So this depends on n, converges as n goes to infinity to 0. That's what we mean by this convergence. So now what we want to show is that and this is something we don't know yet, okay? We want to show that the derivatives, the partial derivatives, alpha partial derivatives of all orders up to and including the order k derivatives exists, and we want to show that the alpha derivative of v is equal to v alpha where, or at least almost everywhere in omega, where this v, we're going to define it this way. It's going to be the unique function in LP where Vn converges to V. Now, how do we know that such a function exists? Well, we know, right? We said a priori that we know that all of these sequences are Cauchy sequences. So I want one in particular. I'm going to extract one of those sequences in particular, and that's the one where the order alpha is equal to 0. So that's the original function itself. So we know that Vn converges to V, okay, in LP. So this is going to be our kind of base level function. And now what I want to do is I want to show, right, because that's the original function itself, no derivatives attached to it. We want to show that this guy is weakly differentiable as many times as I want, up to and including the order k derivative. And I want to show that the partial derivatives of this guy are actually equal to these functions that I know exist from this convergence. If I can do that, then I've closed the loop and I will have shown what I wanted to show. So what do I want to show in order to show or to demonstrate that this is a Banach space? I need to show that every Cauchy sequence converges to a sequence in that space, or converges to a function in that space. What does it mean for it to have converged to a limit point in this space? So if I say Vn converges to V in WKP, that means, in particular, this function here has to be a WKP function. It has to have certain partials. But I also am going to need each one of the partial derivatives, Vn partial derivatives. I need this to also be true. But I don't want this to happen in WKP space. I need this to happen just in LP space. So this is what I need to show. And I need to show this for all partial derivatives of orders up to and including order k. All right, so that's essentially what I've said that I needed to show, okay, where we have this base level convergence. So what we're going to do is use the definition of a weak derivative. Okay, so For all alpha in C0 infinity, these are our so-called test functions, compactly supported C infinity functions, then because each of the Vn's are differentiable, okay, they're alpha partial differentiable for all alpha up to and including the of all orders up to including order k. All right, so that's what we mean by that statement in symbols. Okay, that I can throw this derivative, which is a classical derivative of this function because this is a smooth function, throw it onto Vn. And as I do that, my integration by parts formula definition says you're going to get a -1 for every time you do that. Okay, so every time you throw a derivative over. So in total, you get -1 to the order alpha power. So this is what we mean by weakly differentiable, weak differentiability of order alpha for Vn. Now, and that's because each Vn is itself a WKP function. Now, what I want to show is that that this and this become very close in magnitude. Now, why this function here? I'm going to discuss that in a second. Okay, so I know that this exists. Why? What is this? This is the target function that I know exists from this convergence, right? Because this is a Cauchy sequence in LP, therefore there has to be a limit function in LP. All right, so let's look at this. Okay, this is the difference of two integrals. Okay, part of the integrands are exactly the same, partial alpha phi. So I'm going to combine this into a single integral and use the linearity of the integral. That just gives me that term. Now I'm going to use something called Holder's inequality. And I think you've probably seen a version of Holder's inequality before. So Holder's inequality says that if I have two functions that I'm integrating, something like this, a u and a v, then and u is in LP and v is in LQ, then this function, the product, is in L1. And its integral, in some absolute sense, okay, the absolute value of this is bounded by these functions. Okay, in fact, I can say this with these moved inside. Right, so that's actually a stronger statement. Now, I'm going to use Holder's inequality, which is this inequality here, and I'm going to use it at this location. Now I've got pretty much everything I need. This function is a smooth function, so it's compactly supported for each phi. So there's no problem taking the LQ norm of that function, right? What about this function? Well, I know that this converges in LP to 0 because this difference, well, this sequence converges in LP, so this difference has to converge to 0 in the norm. Okay, so as n goes to infinity, this goes to 0, this stays constant. So that means that these two integrals are getting closer and closer together. Okay, so why is that important? Now let's go, and we've got to keep in mind what we're trying to show here. Okay, now, by the way, so I can also show, so put that in your pocket. I can also show that these two integrals become close to each other. Why is that true? Well, we said that each one of these guys converges to this guy in LP for any alpha that you like. In fact, that's kind of just I could just use the fact that I know that no, no, I could actually that is a kind of separate fact than this one here. So what I know is that each one of these partial derivative sequences converges to something. Okay, so let's put that guy in there, here, right? So I want to show that these two integrals become close together. I can use the same trick. I have two integrals. I'm going to write them as a single integral. Then I'm going to apply Holder inequality. And if I do that, I get that. I know that this difference in LP goes to 0 because of the statement I made up above. In particular, I said this guy is a Cauchy sequence. So it has to converge to something. That something is just that. Okay. Now what I'm going to do is I'm going to put 5.4 and 5.5 together. And I'm also going to use 5.3. So I know that this integral and this integral have to be on opposite sides of each other, but I just showed that this integral here and this integral here are very close to each other. In fact, this integral converges to that integral. Okay, so I can pass the limit on this guy, and it has to converge to that. I can also pass the limit on this one, and I just showed that that guy converges to that. So if I put all those things together, what I have is that statement. Now, what does this statement tell you? Phi was absolutely arbitrary. So this says that each one of these V's is weakly differentiable, and its derivative has to precisely be that. Okay, so these two functions have to be the same in LP. And therefore, this holds true, I should say, for all alpha that has order less than or equal to k. Okay, so I just showed that. But this means that Vn has to converge to V in WKP, and we're done. So this shows, using the fact that I know that the LP spaces are Banach spaces, that the WKP spaces have to also be Banach spaces. And the proof doesn't use too much more than something like Holder inequality and the definition of the weak derivative. As a corollary to that, in fact, a very quick corollary, for any k, these Hilbertian Sobolev spaces, that is, Sobolev spaces with the inner products, are Hilbert spaces because they have to be, well, any Banach space with an inner product is a Hilbert space. Okay, so that automatically tells me that this space where p is equal to 2, these Hilbert spaces where p is equal to 2, are Hilbert spaces. They're complete. Okay. Now, now I'm going to throw a bunch of definitions and tools that I'm going to need ultimately in my analyses at you in kind of quick succession. Some of which we'll probably forget pretty quickly, and some of which will be more useful. So suppose that omega is an open set. Again, the usual case here is going to be, it's also going to be a bounded set. And another usual case is that it's going to have a fairly nice boundary. And we'll talk about that in a minute. Probably in the next lecture, we'll get more into that. Talk a little bit about it today. So it's right now, it's just an open set, but think open bounded with a fairly nice boundary as well. W0KP is this set, which is what we call the closure of C0 infinity in WKP. And if you've never seen the closure of a set before, we're going to talk about that. And whenever P is equal to 2, we have this special notation that H0K is the closure of C0 infinity in the set WK2. Okay, so what do those mean? Well, first of all, I probably ought to remind you what is the closure of a set, or what's a dense set. So let X be a normed linear space and suppose that Y is a subset. Y is said to be dense in X. It's not necessarily a subspace. It's just some set in X. Y is said to be dense if and only if for any X in X and any epsilon, there is a point Y in Y such that Y is very close to X. And how close? It's within epsilon of the point X in the X norm. Okay, so that says that any point that you have in the space, in the bigger space, there's going to be a Y in the subset, which is very, very close to that. So how close? Any epsilon that we'd like to choose. It's going to be within epsilon in norm. So for example, one famous example of this is the Weierstrass theorem, which says that the space, in fact, it's a space in that case, space of polynomials are dense in the space of continuous functions. So I hope you've all seen that from a course on real analysis. And it basically says this, if you give me any continuous function and any epsilon, I can find a polynomial of some order such that the difference between that continuous function and that polynomial is small in the max norm, the infinity norm. That's what we mean by a dense set in that case. Let X be a normed linear space. This is the space and this is its norm. Define X over bar to be the space obtained by adding the limit points of every Cauchy sequence in X. So this space may or may not be complete, but I can certainly construct Cauchy sequences from that space. All right, so if I take Cauchy sequences, I can then ask, well, what are the limits of the points in that space? Well, you might not know, but what we can guarantee is that there's some space out there where those limit points live. I can add them into the set X, and whatever set I get ultimately, I'm going to call X bar, and that's what we call the completion of X. So if X is already a Banach space, then there's nothing to do because remember, every Cauchy sequence is a convergent sequence to begin with. Otherwise, X is a true proper subset, in this case, I guess it's a space, proper subspace of X bar. And X bar is called the completion of X. It's a little bit bigger than X, right? Because what we've done is we've added the limit points. We can kind of think about the real numbers in this way. So if you start off with the set of rational numbers, and I think about taking Cauchy sequences from that set, and I add the limit points in the usual absolute value norm, then the completion of this guy is equal to the real numbers. So you all have seen this or know about this, but you might not have thought about this before. Now, interestingly here, this set Q is going to be dense in its completion. So we always have this, okay? I guess I should have said, yeah, let's see here. I actually want to make that point. This set is always going to be a dense set inside of here, inside of its completion. So let's say it. X is a dense subset of its completion. It's not a vector, it's a overbar. Okay? Again, these are facts from that you've probably seen in a good course on real analysis, but if you've never seen it before, then if you look at this book by Atkinson and Hahn, which is called Theoretical Numerical Analysis, third edition from the year 2008. Then it has, it's either 2008 or 2009, actually, now that I'm thinking about it, I forget. So all of these types of facts are found there. They can be either found in a good course like in 447 and 448, or if you need to pick them up later in Atkinson and Hahn. So I guess this is why at the University of Tennessee we stress you've got to have some base level of analysis. Measure theory isn't precisely needed for this course, but you do have to understand about concepts like Cauchy sequence, convergent sequence, etc. Here's another very, very famous example. The LP spaces under the LP norm turn out to be the completion of continuous functions under the same norm. Okay? And that means that these functions are dense in this space as well. Okay? The LP functions with the LP norm is just the completion of continuous functions under the same norm for all p between 1 and infinity, but not including infinity. Well, actually, I have to put a question mark on that one. I need to check that. I didn't write it, but do I mean not including infinity? And for some reason, I can't quite. I think maybe this is correct, that it's not true for infinity, but I'll have to think about that. Um, okay. Well, no, let me put that there because I'm gonna go check and make sure I update this. Okay. So apart from that question mark, it's true. What's next? So assume that omega is an open set and V is some function from WKP. Again, these are facts that we'll need, but we're not going to go through the proofs of these. We're just jotting them down so that we have them in our pocket for later use as students of numerical analysis. Suppose that V is a WKP function. Then there exists a sequence Vn of C infinity functions that are also WKP. So what does this mean to be in both spaces? So they're in C infinity, but this is the type of C infinity which doesn't include what happens at the boundary because there's no overbar. Okay? We're not saying what happens at the boundary. So C infinity functions may not be in WKP. So I can't just use functions from this space. I need to require it's in both spaces. Okay? So the intersection is going to be subset of both this space and that space. The intersection is both a subset of this space and that space. Okay, I'm saying I need both properties. I need them to be C infinity functions, not necessarily including what's happening at the boundary, and I also need them to be k times weakly differentiable, such that the weak derivative is an LP as well. Okay, so there exists a sequence of functions of that type such that Vn converges to V, or in other words, in the Kp norm, Vn minus V converges to 0 as n goes to infinity. So in this sense, we say that this set is dense in WKP, right? Because what I'm saying is for every V, I can always find an element from this set which is epsilon close. Now, why does that relate to my definition of density that I had earlier with its epsilons and deltas, or just epsilons, I guess? Well, because this is somehow related. Okay, if we're really converging to 0, then there's some n such that this difference in norm is less than epsilon, and that's what I really need. Okay, that was my epsilon definition up here. So if this is true, or I should say this is true if and only if I know that this is dense in that space. All right. notice that we're not demanding that these are C infinity functions. I should say, let me say it like this. C infinity omega is not the same as C infinity omega bar. Why? Because it's kind of easy to it's kind of easy to see. These functions here do not have to be bounded, right? Because this is an open set. This is a closed set. In fact, closed and bounded generally. I'm going to make this guy usually be open and bounded, and therefore its closure is closed and bounded. So therefore, what we call compact. So when this is a compact set, each one of the functions of this space is going to be a bounded function. In fact, all of its derivatives are bounded. Okay, all orders are all bounded. So this space, not necessarily true. Okay. One such example of that is, or you can, an example related to that is the fact, well, let's say it this way. So the function f of x equals 1 over x, right? So this guy is in C infinity of 0, 1, right? All of its derivatives exist and are continuous on the interval 0 to 1. But it's not even true that f is a C0 function on 0, 1. There's nothing I can do to make that true, right? Because this guy's blowing up. It's not a bounded function. Okay, so the discussion that I had above is related to a fact like this. Okay, this guy is definitely, this is a function that's in this space, but it's not in this space. Definitely not. All right, we'll do these couple results and then we'll take a little pause and take some questions. So suppose that omega in RD is a bounded open set with a Lipschitz smooth boundary. So a Lipschitz smooth boundary means that the boundary has a fairly nice shape. It doesn't have any super bad places on it. Like for example, it doesn't have any places where there are sharp points or sharp cusps, I should say. Now it can have angles on the boundary. What it means is that if I say that the boundary is Lipschitz smooth, what I mean is I can rotate that set. I can rotate the set in any way such that when I think about one part of that, okay, as a simple function of x, I'm going to rotate it so that I can look at some spot of the boundary where it's a function of x. So loosely speaking, this is going to be a Lipschitz function. So it's a function that is not necessarily smooth, but it's continuous and it has other nice properties. For example, the square root function is Lipschitz continuous. But for example, there are some functions out there which are not Lipschitz continuous. And let me exhibit one which is not. So let's take the square root function and add to that on the other side the square root of minus x. So this function, f of x, is going to be equal to the square root of x whenever x is greater than or equal to 0. Okay, and then whenever x is negative, we're going to take the square root of minus x. So that's that function right here. That function's not Lipschitz. It has a nice sharp corner right there. Okay, and so there are functions out there which are not that nice. We're saying our boundary has to be, whenever I do proper rotations of it, every point of the boundary has to be a Lipschitz function. It has to be fairly decent looking. Some functions, well, some boundaries don't have this property. And for reasons that I won't go into, we're going to exclude those. Suffice it to say, sets whose boundaries are Lipschitz are fairly nice, and they're nice for our purposes. I keep forgetting to hit the right button here. Where's my delete? There we go, delete. So let's suppose that omega is a bounded open set with a nice boundary, Lipschitz smooth boundary, and suppose that V is in WKP omega, then there exists a sequence of C infinity functions on or over omega bar. So this set here is closed and bounded. Okay, so these are really, really nice functions, kind of even nicer than these functions here. And the reason is because this is in WKP for any order that you want. Okay, so these are super nice functions. There exists a sequence of those functions such that Vn minus V Kp converges to 0 as n goes to infinity. So this says that these functions are dense in WKP. Or in other words, WKP is just the completion of C infinity omega bar with respect to that norm. Either way, it means more or less exactly the same thing. Okay, and this is related to the definition that we made earlier. In fact, it's really just a restatement. Falls out right from the definition. If you remember how we defined these functions, so for any v in this function class, then there exists a sequence Vn of compactly supported C infinity functions such that Vn minus V in the Kp norm converges to 0 as n goes to infinity. Okay, so in other words, these functions are dense in these functions. And in fact, that's by design because we simply said this set here is the completion of these guys under that norm. So it means all the same things. So why are these results important? The reason they're important is because, oh, by the way, one important point here that I wanted to point out is that this set here does not have to be bounded, and it doesn't have to have a very nice boundary at all. It just has to be an open set. I guess I should have said that. Probably should add that later on. Omega is open. Okay, so it has to be fairly nice, at least open, but it doesn't have to be bounded. It doesn't have to be Lipschitz continuous. This tells us whenever we have functions from these various function spaces, that we can get very close to them with functions which are a lot nicer. Okay, so these functions are kind of weird and mysterious, but I can always get very, very close to those functions with functions which come from these very nice spaces and which themselves are very, very nice. Okay, so these are what we call density results. So put those in your back pocket. They're going to be very useful to us as we do finite element work. So the next topic I want to talk about is Sobolev embedding theorems. It looks like with how much time we have, we won't get through all of this, but at least I will be able to explain to you what are embeddings, what we mean by embeddings, and why the heck they're useful. So it turns out for Sobolev spaces, if the k number and the p number are high enough, then the functions inside of those Sobolev spaces actually are like functions that we know and love and are much more familiar with, namely LP and continuous functions of certain orders. So the Sobolev embedding theorem tells us whenever k and p are large enough, their product is large enough. Remember, both k and p are positive real numbers. Whenever k and p are large enough, then the functions of the Sobolev spaces are actually nicer functions that we're much more familiar with. Okay, but this is true in some sense, which is called an embedding. So I have to tell you what an embedding is. That's a very practical result, and I'll give you lots of examples, but you need to know what an embedding means first. So we say, or we start off by assuming V and W are two Banach spaces, and V is a subset or subspace of W. We say that the space V is continuously embedded in W, and we write V hook right arrow. That's what it's called in LaTeX, hook right arrow, or V is continuously embedded. That's easier way to say, easier than saying hook right arrow. V is continuously embedded in W. Okay, and what that means in symbols is that there exists a constant greater than or equal to zero, greater than zero strictly, such that the W norm of V is less than C times the V norm of W. Sorry, said that wrong. The W norm of V is less than C times the V norm of V, okay, for all V and V. That's what it means to be a continuous embedding. I'm going to show you a way that makes this easier, I hope, to remember. We say that V is compactly embedded in W, and we write V hook right arrow W. Okay, so what this means is compactly embedded in W. V is compactly embedded in W if and only if it's continuously embedded in W. So that's the first statement. It has to be continuously embedded. So that's that part. So I'm just restating that part. And for every sequence V and V that is bounded, there is a subsequence. Everybody, I hope, knows what a subsequence is. A subsequence drawn out of Vn and a point V in W such that Vnk converges to V in the W norm. And this should say as k goes to infinity. As k goes to infinity. Okay. Now, if you've ever studied a little bit of operator theory, some of you were in my class 547 a few years ago, and we studied operators, and we studied embedding operators. So all this means is that the embedding operator is continuous. And this means that the embedding operator is what we call compact. How in the heck do you remember these definitions and what they mean? Well, first of all, we have to have V being a space inside of W. Okay, so if V is in W, then there's a standard mapping that goes from V into W. It's called the identity mapping, sometimes also called the embedding mapping. So, okay, there's the identity. What does it mean? It means I'm going to take points from this set V and I'm going to map them into W just by making them themselves, right? And this is exactly what it means to be a subset, okay? It gets mapped into W by just being itself. So really it's going in there. It's going right back to itself. I is the embedding operator, also called the identity operator. For a mapping to be, for an embedding or any other mapping to be a continuous operator, it has to satisfy this property. I of V is less measured in W, because remember, I of V is over here in W. I can look at a point V. Actually, let's give it a different color. All right, we have the point V, and it goes over here to I of V. Right? So I of V is actually in W. I of V is in W. That has to be less than a constant times the V norm of V. So that's what it means for the embedding operator to be a continuous operator. Now, compact operators, so first of all, why did I drop the I here? Well, it's the identity, okay? It's just the identity. So if you can remember what it means for an operator to be a continuous operator, that's what that part means. And then, of course, just remember that it's for the identity operator, so I drop the I, and that helps me remember that it has to be this way, this space W over here and this space V over here. Compact operators are an important class of operators. We're not going to use this too much in this course, so do not panic about not knowing what a compact operator means. go give it a wiki or a Google, figure out what a compact operator is. It's a very useful thing. It tells us something in addition to the fact that we have a continuous operator. What it says is if I have a bounded sequence in this space, then there's a subsequence and a point W such that a subsequence of that converges to a point in W. So I might start off with a sequence and I don't know all I know is that it's in V, but I don't know if it has a point to which it converges in V. However, I do know that it has a subsequence that will converge to a point in W. And that's a very powerful statement. It's a very important and powerful statement. And I'm going to give you an example next time when we come back of what that means and why it's useful. But before we get there, I'm going to confuse you a little bit further by introducing these so-called embedding theorems, Sobolev embedding theorems. And the reason why we need them is because it tells us when a function from WKP actually is a bit smoother than what we expected, okay? Or it's nicer than what we expected. Okay, so suppose that omega is an open bounded domain, and in this case, it has to have a nice enough boundary. It has to have what we call a Lipschitz boundary. Remember, Lipschitz boundaries means that it doesn't have those cuspy points like the same way that the double square root function has. Then the following embeddings are valid. Okay, we're going to look at continuous embeddings first. We won't get along to the compact embeddings because we won't have enough time. Okay, so we're on a nice open-bounded Lipschitz domain. If K and P are not quite big enough, they're not going to be bigger. The product is not going to be bigger than D, or in other words, K is less than D over P. Then these functions we can show that they're kind of related to functions which we're much more familiar with, but only up to a certain value of Q. So what we want to say is that these functions are, remember, continuously embedded in LQ. That means that it has to be a subset of LQ, and there has to be, well, there's two parts to that, right? It has to be a subset, and it has to have this continuity of the embedding operator. Okay, so this says that these functions are actually, the main point here is that they're actually LQ functions for any Q less than P star, where P star is what we call the conjugate Sobolev exponent. Okay, conjugate Sobolev. I want to rewrite that. Actually, I want to rewrite this too. Let's slow down here. Conjugate Sobolev exponent. That's what the P star is. And it satisfies this little equation here. So this, I'm going to give you an example. It's probably going to be impossible to remember all these facts. I don't want you to remember the details. I simply want you to know how to apply them. I'm going to show you how to apply them momentarily. This is what we call the critical case. If K is exactly equal to D over P, or in other words, K times P is equal to D, then WKP is continuously embedded in LQ for any Q, no matter how large it is. Okay, so this says that these functions are actually going to be Lebesgue LQ functions of any order that we like. So those are functions that we know and understand. Now, the good news is if I keep increasing the value of this product K times P, and at some point KP is going to exceed D, that means that that either k is really large or p is really large, or maybe our dimension is small. But either way, if the product kp is large enough, strictly bigger than d, then actually these functions are are a subset of continuous functions. Now, you've probably seen these functions called Holder continuous functions before, or talked about them. I don't really care about this Holder exponent here, so we're not going to worry too much about this. The thing that I'm mostly interested in is this part here, the fact that these functions are going to be continuous of a certain order. Now, that means that all of its derivatives, okay, the function and all of its derivatives up and including whatever order this is, um, are continuous functions. And I think I said that wrong. The function and all of its derivatives up to and including whatever order this is are continuous functions. Now, what is this order here? Okay, this is k. Of course, we know what k is. K is a simple positive integer. This, it means the largest integer, okay, bracket x is the largest integer less than or equal to x. So this is some integer that I'm going to subtract away from k. But since this this is less than k, this thing that I'm going to be subtracting away is still less than k. I'm going to subtract one more, and this is just going to be some number, some positive integer. That means it's a continuous function of that order. And the other nice property is that it's over this compact set omega bar. Because remember, omega is an open bounded set with a nice Lipschitz domain. If I take omega bar, then that's a compact set. Okay, so this is the most important part about it here. Don't worry about this extra, this, these are what we call Holder spaces, and this is what we call the Holder exponent, I guess. So don't worry about what that part is. Really just interested in this part. Let me tell you how these results are applied. And let's start with this case here, because this is the best case. What it's actually saying is these Sobolev spaces are actually spaces of continuous functions, that everything in there is a continuous function. Okay. Now, it requires a little bit of interpretation, so let me give that to you here. And I guess we'll only get this one example done. Suppose that d is equal to 1, and let k be any positive integer greater than or equal to 1, and p be greater than or strictly greater than 1. Okay? So that means that my product, kp, is strictly greater than 1, which is my dimension. So we're in this case here. We're in that case here. I could go ahead and compute what this is based on the size of k. I'm not going to do that. We'll just say to ourselves, well, at least we know that this is going to be greater than or equal to 0. So for any of those exponents that, or any of those numbers that we want, kp is strictly greater than d. So that means that wkp is continuously embedded in continuous functions. In fact, actually, there's some more stuff in there, but I don't have to worry about that. So what does this mean? It means that these Sobolev functions, these Sobolev space functions, are actually continuous functions. They're inside of the space of continuous functions. Plus, there's that extra little bit about, VKP, or no, let's see. This is going to be continuous functions, right? So this is going to be, what is the usual norm on continuous functions? It's going to infinity norm is less than a constant times VKP. Okay. So there's also that bit, which I'm kind of neglecting. Now, remember, these functions are Lebesgue functions. They're basically Lebesgue LP functions, and we said that, these functions, if I scramble up their definition on a set of measure 0, it doesn't mean anything. It doesn't, there's nothing lost by changing their definition on a set of measure 0. So how do I interpret those functions in light of the fact that I'm saying that they're continuous functions? Well, what I'm saying is that these are actually somewhere in the class of equivalent functions that differ from functions here on a set of measure zero. There is one of those functions which actually is continuous function. Okay, so that's what I mean. Um, and I won't, you know, that's why I say it takes a little bit of interpretation. So if you know about LP function spaces and you know this property about them that you can change their definition on a set of measure zero without altering them in any essential way, then you might wonder, how am I going to make sense of the fact that these functions, which I can change here and there as I please, are actually going to be continuous functions. Continuous functions, I thought, it really matters how they're defined everywhere. And that is true. I have to give you a little bit more interpretation about what this means, and I have to talk a little bit about equivalence classes of functions, etc. But we'll get into that next time. The other thing I'm going to get into next time is a few more examples. I'll leave this in the set of notes for lecture 5. You can look through them, or I'll put them in the lecture 6 notes. But in any case, you can look ahead of in there. But I have to put a little asterisk here. I still need to help out with this interpretation and what this means. Right, so we'll pick up at this point next time, and we'll end the lecture there.